So his work is primarily focused on the use of microwave remote sensing for the study of the cryosphere and tropical ecosystems. And today he'll talk about remote sensing physics and measurements, providing an overview of the measuring capabilities of different sensors, such as active and passive microwave, LiDAR, and solar-induced fluorescence. So please help me welcome Professor McDonald.
Thank you. So actually, I'm going to stick to the active microwave part of using radar. I'm not going to cover the passive, because when I was going through things, I realized, as Janine had mentioned, you teach entire courses on each of these. And when I learned microwave remote sensing, it was like a 3-semester series that I did. So you can't really do it justice. One of my favorite quotes here is shown on the right from Lord Kelvin, which was actually in my freshman electromagnetics test, not freshman, but undergraduate electromagnetics text when I was an electrical engineer. It's grown on me as I've got into the remote sensing field, because much of what we do with these kinds of technologies actually have their roots in physics and what we call first principles. So a lot of us are used to dealing with these products, but there's a lot of information content, and there's actually first principle information that is in those products, and actually to fully exploit them, you really need to go back to understanding quantitatively what the information content is. So I'm going to show a little bit about how each of these technologies work. LiDAR and SIF, I had contributions from others, and radar, I drew a lot from the RSET program from NASA to show some of the introductory stuff, and I'll show some examples here. So talking about radar to start, we're looking in imaging radar in particular is what I'm going to discuss here. The concepts of radar is it's an active sensor, meaning it transmits its own source of energy, a coherent waveform that propagates through space and interacts with the media that you're trying to characterize. The energy will then scatter generally in all directions, and some of that energy will come back to the sensor, and this is the case for what we call a monostatic radar, meaning the same radar transmits and receives energy for imaging, and we call that backscatter because it's energy scattered back. So a monostatic radar, the typical imaging radars we have in space, can only measure the part of the echo reflected back toward the sensor. The sensor energy, the wave energy, travels at the speed of light. You can use this information to infer what part of the target you are seeing based on the time and velocity relationship. The strength of the signal that comes back and the character of that scene that you're trying to image is contained in a quantity we call sigma naught or sigma 0, which is the backscatter coefficient, and it's expressed in decibels, which is a logarithmic scale related to power content. It's important to note that radar transmitting a coherent microwave pulse or a continuous wave in some cases is a coherent sensor. So there's coherent energy here, meaning that the waveform that you transmit has a phase relationship relative to, say, a companion radar or a different antenna transmitting with a fixed configuration with it. And we can use that information in phase to get a lot more information out of the scene. That's the case with interferometric SARs, and I'll show a couple examples of that. It also leads to some interesting features in the radar scattering statistics. So why use microwave anyway? This is a depiction, courtesy of Paul Rosen at JPL, of atmospheric opacity throughout the electromagnetic spectrum here. This is wavelength here, and this is the opacity of the atmosphere. And we see, if we look at the atmosphere in the visible portion where our eyes work, we have a window where electromagnetic energy is able to propagate through the atmosphere. Similarly, in the microwave region, the energy is largely unaffected or minimally affected by atmospheric conditions. So we're able to use these windows and observe the surface, the Earth's surface. These are some of the operating and planned synthetic aperture radar missions for spaceborne use. And we use various wavelengths indicated here in terms of wavelength for the different bands we call. So us radar folks you'll hear us say L band, C band, things like that. We're really referring to these wavelengths that are used. And you can use information about backscatter from different wavelengths to infer different character of what you're observing. The other thing I want to point out here is that in the microwave region in particular, radar energy is largely unaffected by clouds. So we have the ability to do imaging of the ground surface independent of cloud cover. And since it's an active sensor, we can image day and night. So in terms of physically interpreting backscatter signatures, you can sort of boil it down to looking at various scattering mechanisms. And these are all derivable mathematically if you go back to first principles, Maxwell's equations, the wave equation, those sorts of things, and solve various approximations that look at the propagation of energy in complex media. You'll actually have these terms sort of fall out of the equation. But you get single bounce scattering, what we call surface scattering, commonly seen on rough surface areas. You can get volume scattering from, say, a vegetation canopy where the energy interacts with a volume of media and scatters within it, and then some of it comes back to the sensor. And often in certain structures, like where you have buildings or where you have forests with certain vertical structure associated with it, you can get this dihedral reflection, which is a double bounce mechanism. This can actually dominate the radar backscatter signature under some conditions, largely because of the coherent nature of this scattering mechanism with a sort of this double mirror effect. And we can look at some examples. This is the data from the SMAT mission, Soil Moisture Active Passive, from 2015 when it was launched. It had a radar on it. Unfortunately, the radar only functioned for about 2 or 3 months, but we got a really nice global data set of L-band backscatter. And this shows the main stem of the Amazon here, but you see various features through the Amazon forest. And I'll point out a few of these. Over here, you're seeing very dark areas along the river. This is indicative of what we call specular scatter, which comes from very smooth surfaces such as water surfaces. So it appears very dark in the image because very little, if any, energy actually is scattered back to the radar. So water, open water, looks very dark. When you get sort of rough surface conditions like you might have with tilled soil or some agriculture areas, you get scatter in general that is going off in more directions, and some fraction of that comes back to the radar, and you get sort of an increase in the backscatter over what you see in water. And that's still a surface scattering mechanism. Then for volume scatter, especially when you have forests like you have in the Amazon, you can get a significant amount of energy that interacts with vegetation volumes and then comes back, and those are a little bit brighter still. This is a volume scatter mechanism. And then for the double bounce, what you're seeing here are these bright areas which have basically an inundated areas underneath vegetation canopies. Since the radar has it has a long wavelength sensor, it interacts with the medium, the scattering medium, for scatterers sort of dependent on the size of the wavelength scatterer relationship. I'll talk a little bit about more of that in a few minutes. But if you have a water surface here, remember you get a very strong forward scatter where you get the dark regions here of open water. But that forward scatter then can interact with the vegetation, and then some of that scattering coming from the water to the vegetation comes back to the radar. This is that double bounce or dihedral reflection effect, and it can lead to a very pronounced dominant signature. So the ability to image things like inundation under vegetation, look at soil moisture and those sorts of things because of penetration through some of the overlying vegetation is really unique to radar and microwave in general. The other aspect of radar that is of critical importance, or another one, is polarization. So radar signals being coherent, we have a control, we can control the polarization of the transmitted wave, and we can also receive polarizations in different configurations. What the polarization refers to, it's simply the relative direction that the electric field vector points relative to the wave propagation. So horizontally polarized energy has the electric field vector pointed basically horizontally to the surface of impact. Vertically polarized, this is horizontal here, vertically polarized energy will have the electric field vector pointed vertical to the surface of what it's scattering from. So you have horizontal polarization and vertical polarization, and they will interact with the medium and the scatterers in the scene in different ways depending on the orientation of the scatterers in the vegetation canopy. And you can use this information to determine physical properties of the objects observed in terms of polarization. As an example of that, these are data from the NASA JPL UAV-SAR, aircraft-mounted L-band imaging radar. We acquired some data there over the Pacaya Samaria Forest Reserve in Peru a few years ago, and we're looking at 3 different polarizations, HH, VV, and then cross-pol, where we transmit horizontal and receive vertical. So this is transmitting horizontal, receiving horizontal, transmitting vertical, receiving vertical, transmitting horizontal, receiving vertical. And so the dark areas, here's the river channel, and there are various kinds of vegetation communities. It's a huge wetlands complex here. So these are all in grayscale. So how do we kind of look at the relative importance of the different polarizations? A common way to do that as a first cut is to create a false color composite where you assign different colors to different polarizations, and then the different colors and the mixes, the blends of the colors will give you some idea of how the landscape backscatter responds in terms of polarization. So you can see you can get a very wide variety of signatures relative to the different contributions of the polarizations. The green areas tend to be dominated by the volume scatter component that we talked about, and the red and blue, HH and VV, will be more indicative of inundation under various kinds of vegetation structures in this particular scene, which is in the wetlands. So where does that all come from? How can we kind of explain that to a higher level? Well, backscatter interacts with surface media relative to different properties that are related to structure and what we call dielectric constant, which is an electrical property of the scene. So you can think of vegetation density as having a large effect. When we talk about using different wavelengths in particular and how the backscatter or the microwave energy interacts with the medium, you're really talking about the size of the scatters relative to the wavelength. So small scatterers, leaves, those sorts of things will have a minimal effect at large wavelengths, but a big effect at short wavelengths. And when you're talking about large, long wavelengths and short wavelengths, you're talking about that size relative to the scattering constituents. Shape and orientation, we talked a little bit about that double bounce mechanism. Or vertical structure, like you get with tree trunks, tend to give more rise to like this double bounce curve term that we saw. Leaves will give more diffuse scattering, more of that multiple scattering component where you get a lot of cross-pol generated. And so we can use the polarization to look at shape and orientation. there's effect of how dense the vegetation is in terms of how much penetration we can get, and it all relates to size of the scattering constituents relative to wavelength. We have this electrical property here, dielectric constant, which relates to basically the water content. It's highly affected by amount of water because water, being a polar molecule, has a little dipole moment that is highly reactive to microwave energy. So the water molecules will oscillate when they're interacting with the microwave energy. And we measure that through this term, the dielectric constant. More on that later. In terms of structural components, you might consider what we see with a different, with a given kind of vegetation canopy at different wavelengths. So X-band, you're looking at a wavelength about 3 centimeters, L-band 23, P-band 70. For a given tree, as you go to longer and longer wavelengths, the tree becomes a little bit more transparent. You're seeing different aspects of structure. And this is just showing that graphically. And we can use that to examine, for example, biomass as a function of, the backscatter as a function of biomass. Here we're looking at 3 different frequencies. C-band, that's about 5 centimeters, L-band 23 centimeters, P-band, the longer wavelength. And we see this backscatter biomass curve in each case, and we see that this curve tends to saturate at different levels of biomass depending on how long or short the wavelength is. So the longer wavelengths, we get more sensitivity to biomass, up to about 100 tons per hectare when we reach the saturation point. On the other side here, C-band saturating at about 20 tons. Another aspect is how much penetration we get associated with different frequencies looking at vegetation. As an example of that, we can look at these airborne data looking at C-band and P-band over a forested area with some complex here, and you see very different features. This C-band is more reacting to the vegetation cover, and I draw your attention over here where you're seeing almost no difference between these regions. But over here at P-band with a very long wavelength, again, these are false color composites, you're seeing a very different VV backscatter dominated signal here that's related to the penetration of the longer wavelengths into the canopy. This is a nice example. It's one of my favorite scenes that was acquired by NASA's SRTM imaging radar that flew on the space shuttle some time ago. But this is a false color composite that combines L-band and C-band information. So you're looking at multi-frequency data here with 3 different polarizations. This is the Karasoke region, Central Africa. You have these volcanoes. You see a lot of variation with the volcanic flow and vegetation cover. But to draw your attention to this little green stripe here, which is dominated by C-band HV, this is bamboo forest. And it really stands out here, but that's the habitat of the mountain gorillas. So you know, it was stunning to me when I first saw this that the simple false color composite can pick out such a critical habitat area. Now we talked about dielectric constant a little bit. I'm going to say a little bit more about what we can use that for. Basically, if you look at dielectric properties of natural materials, water pretty much dominates because of its polar nature. This is an electrical property of the molecule that relates to its dipolar construction. So you see dry materials, rocks, soil, vegetation, have very low dielectric constant. Liquid water has a very high dielectric constant in the microwave region. For this effect, because radar is sensitive to dielectric, we can look at the amount of water as it changes within a medium and do things like look at soil moisture, vegetation water content, things of that sort. And you can also look at the state change of water as it changes from frozen to thawed conditions, for example. So you see here dielectric constant is a function of frequency. Ice is very low because it's essentially the molecules are frozen in a lattice and cannot oscillate freely. Once they transition to a liquid state, you get the very high dielectric response. You can look at time series data. These are data acquired over Bonanza Creek Experimental Forest near Fairbanks, Alaska. You can use time series change detection techniques to look at the thawing of the landscape, and that's manifest here just as a brightening of the backscatter as we go on. And you can run some more sophisticated algorithms to actually look at thaw, freeze, melt processes. These are examples from the high mountain Asia domain looking in the Himalayas, where we have used C-band radar, ASCAT, and Sentinel-SAR. ASCAT's a coarse resolution scatterometer, runs at about, we have data here from about 4.5 kilometer resolution. The Sentinel-SAR is much higher resolution, and you can look at the difference between having the fine scale and the coarse resolution products and see the importance actually of getting the high spatial fidelity here in these complex terrains. What we're using these data for is to quantify the melt and freeze processes, not only of the seasonally snow-covered land in these areas, but the snow melt and ice melt processes on glaciated areas. And we're studying how that feeds into stream flow and relates to hydropower generation. So this is a fine example where we can use multiple sources of different kinds of radar to look at that time series seasonal melt and tie it in with some critical processes, even to socioeconomic levels. And looking now at some data from the Japanese Pulsar-2 instrument. These data are courtesy of JAXA. These products were developed by a student in my group, actually looking at the Amazon basin here over 3 hydrologic years and quantifying maximum inundation extent during those time periods. We're looking at the full Amazon here, the blue sort of areas. We're looking at inundated vegetation versus open water, also seasonally submerged vegetation, and areas not flooded or in green. And so we're looking at the full basin in this case, and then the region of the central Amazon, where you have the Negro and the Salamoas converging here around Manaus, and that's in this area here. And then we also have some studies we're doing in Pacaya, Samaria, the big wetlands complex that's in the upper Amazon here. So we can look at this to quantify hydrodynamics. And then I wanted to mention this. This is work done by Kat Jensen in my group that we've been working with Erica on actually here at JPL. We're using data from the GPS constellation. This is a NASA mission Cygnus, which is a set of receivers that fly in a low inclination orbit focusing on the tropics, but it's measuring GPS reflections. So this instrument, we talked about this specular scatter term that came from smooth surfaces, and you get forward scatter coming from that. We don't get so much backscatter, but you get scatter in this direction. Cygnus is essentially a set of receivers that's geared to quantifying this reflection. So it's a bistatic radar receiving a different kind of a signal, and it's looking at a different set of scattering statistics. And we relate that here to an imaging radar-based classification that we derived. And we're seeing a lot of promise in these emerging technologies to take advantage of those kinds of things. Now, I mentioned earlier about the coherent nature of radar, having that phase relationship and the transmitted energy relative to what's received. And that phase statistic actually leads to this speckle feature. This is a granular noise that's inherently present in all radar data because of the coherent nature of the measurement. If you were to consider a uniformly flat area with a little bit of roughness and just look at the radar signature imaged over that region, you would see scintillation in the image. That's what this speckle is. And this is a relation, this is related to the constructive and destructive interference and combinations of various kinds of interference between the coherent energy scattered from different points in the scene. You can get areas where it's very bright, where you have constructive interference, and you get sort of this salt and pepper effect where areas that are very dark have destructive interference with the neighboring scatterers. We can handle that by various kinds of spatial or temporal smoothing filters, but speckle is very well defined. We know, it's a Rayleigh distributed process. We can show that. So we know the statistics of speckle, and we can handle it in various ways. But so those of you who've looked at grayscale radar data may wonder where the speckle comes from. That's where it comes from. But we can also use that phase relationship to do techniques of radar interferometry. So if you have, since radar is a coherent source, if you have two radar antennas that act as coherent point sources, then they're propagating radar energy along these planes of propagation, and what scatters back, you will get various kinds of wave fringing effects. You can basically generate an interferogram from the two SAR images that you get, and that looks something like this. It's a standard radar image. This is an interferogram generated from an interferometric radar. So an interferogram, it has a magnitude that's related to correlation between the two radar waves, and its phase is related to the geometry differences within the scene. And you can use that information if you have two antennas like we did with the SRTM mission, the Shuttle Radar Topography mission, to collect data from these two antennas, create your interferogram, and then you can generate a digital elevation model. Now, SRTM generated a very nice digital elevation model. It's in wide distribution. It's used all over the place. But one thing to point out, what we learned from studying radar backscatter in the previous material, is that you're getting various levels of penetration into the vegetation. You're getting various interaction mechanisms that occur. What you're seeing here in terms of the digital elevation model isn't really what we would call a bald earth model. It's more of a imaging of where the scattering energy is dominated from within vegetation canopies. So if you have dense vegetation and you don't get a lot of penetration of the radar energy through there, you're really seeing a topography measure that's measured somewhere in the tree canopy. So that's just something to take into account when you're using these DEMs. Differential interferometry, this is time series technique where you can fly a radar in a repeat pass kind of a mode, and then if you collect your data and generate your interferogram, you can look for surface motion. This is associated with faulting and earthquakes in this example. Radar data acquired at two different times, pre-earthquake and post-earthquake, can measure things like displacement associated with the tectonic activity. Now I'd like to move into talk a little bit about LIDAR. So radar is microwave energy, so it's radio detection and ranging. LIDAR uses lasers or light energy, light detection and ranging. So the basic principle is that you're using a laser to measure the distance between the sensor and various scatterers on the ground. LIDARs are active sensors just like radars, but they are optical sensors, so they have difficulty with cloud cover and those sorts of things. But there's a couple different kinds here. There's discrete return LIDAR, where basically you're looking at point scatterers and you derive as a product what's termed a point cloud. So you get data that are in XYZ coordinates, and you can look at surface structural features that way. Full waveform LIDARs basically digitize this waveform over the region, the footprint of the LIDAR, and you get a profile. Okay, so the advantages of this technique are you get more horizontal detail, but it's a lot of data to deal with. The full waveform approaches, they give you more vertical structure information and less horizontal information. So you can use those kinds of like waveform LiDARs in this example to look at the shape of that waveform, how it relates to structure in the canopy and understory, and you can come up with a biomass relationship, estimating biomass from combinations of metrics that are derived from the waveform. And this is an example of different kinds of vegetation structures and what you can see with the waveform. We can pull that in, and some examples of how this has been used in the realm of niche modeling, looking at delineating tree crowns and various crown area weighted height metrics, tying it in with other remote sensing data sources from optical and radar and ground surveys of bird occurrence, and then come up with some habitat maps. It's an example there. Another one example here from Mark Samard and Naira Pinto, their work on habitat fragmentation, looking at various LiDAR data sets combined with radar in this case to come up with a contiguity index for habitat fragmentation. The last topic I wanted to go through very quickly, because I see I'm on red, I wanted to mention CIF, chlorophyll fluorescence. This is a really promising sort of newer spaceborne data set technique. The concept here is that you have photosynthetic processes going on at the leaf level. They're driven by the photosynthetically active radiation. Excess photons that are not used in that process are dissipated as heat and fluorescent light. Physiologists have long looked at this using the pulse amplitude modulation or PAM technique to look at these processes at the canopy level. But now we have capability to look at this from space. The challenge in doing this, I borrowed these charts from Christian's talk at KISS a few years ago, actually. These are fluorescing vegetation samples. You can look at the fluorescence in a dark room in the lab very easily, and you do have this signal here. But out in the natural environment, it becomes more difficult because you have incoming radiation from from the sun that interacts with the medium, and then you get your reflected radiance, but you get this fluorescent emission, which is very, very small relative to the amplitude of what's coming out from the reflected radiance. So what you have to do is go to you go to portions of the spectrum where you have where the atmosphere it absorbs a lot of the optical signal, so you're left over with the fluorescent emission to try to get that. And you can get this, you can look near the O2 lines where you have a lot of absorption, and you can get above canopy fluorescence because it occurs at a little bit different. Well, there's some stuff I don't have time to go into, teach a whole course, but anyway, you end up with fluorescence being related nicely to gross primary production in this example. These are CIF measurements at a site in the Harvard forest. We get a very nice fluorescence signal that is correlated with the productivity there. And this is an example that I got from Christian also, looking at cornfields, comparing something like the NDVI, the Normalized Difference Vegetation Index, which is a spectral measure of vegetation robustness, if you will, against fluorescence on this side. And you see for the different cornfields, you get different relationships between these two. So although you're looking at kind of similar processes, this is an example where you can probably use these information synergistically because there's additional information being provided with using fluorescence in combination with the difference index. So how do we measure this from space now? Because we have that absorption by the atmosphere, well, what we do is we go to the Fraunhofer lines. These are the sort of holes in the solar spectrum that are related to the solar spectrum not continuous in a black body sense. You get these sort of empty spots in the spectrum of the sun that correspond with the absorption of various of light energy as it's emitted by the sun by various atoms that are present. And so if we look in the Fraunhofer lines for the solar fluorescence, we can then get, this is a video it's going to run, we can then get a measure from space of the fluorescent signal. And this is an annual product comparing SIF and gross primary production from NDVI. And we're getting, is that running? I can't tell. It's not. I think, okay, there we go. So you can see the green up processes in the springtime. Lots of promise for using SIF for tracking net primary production. I refer you to this paper by Christian for looking at these kinds of series. It appears that SIF is capturing the seasonal patterns in gross primary production better than the more traditional NDVI measures. NDVI is more of an index. I think there's a lot of really innovative work that can be done to look at these physiologic processes at the plant level to understand that information content. So along those lines, I'll wrap up with this. These are 4 sensors that are either flying or to be flown soon on the International Space Station. OCO3, EcoStress, JEDI, which is a continuous wave LiDAR, SUI, which is a spectrometer. I think Phil will cover spectrometry after the break. EcoStress. Anyway, these primary measures from each of these instruments relate to a variety of retrievables, and there's significant amounts of synergism between these sensors that can be brought to bear in order to more fully characterize physiologic processes in the vegetation, which is really what I'm interested in getting at myself. But these are just what's flying on the space station. We have other sensors like NISAR is the NASA ISRO SAR that's going to launch in a couple of years. There's a variety of other instruments that are planned. So our challenge then is to move forward in the context of how to use these things synergistically to optimize the kinds of processes that Janine was talking about in her talk. So with that,
Thank you very much.